So we come now to acceleration analysis. The question that we ask is, relate the acceleration of a point P in two coordinate systems. So on the right you see a figure that you have seen previously in lecture 9 in the context of velocities. What you have is you have a coordinate frame here in the red, in which the motion of point P is being observed. At the same time there is another coordinate system in blue, possibly the body fixed coordinate system of some rigid body, and this coordinate system E, which can be possibly changing and rotating and tumbling with time, is also observing the point P. And what we want is, we want to relate the observation of acceleration by the rotating BFCS E to the acceleration observed by the observer coordinate frame in red, E0. P's acceleration in the BFCS E is given by AP E, which I start writing as AP rel, and the BFCS, which is attached to this rigid body B, is rotating with respect to the observer at the angular velocity omega b, which I have written here. But now, because we are considering accelerations, we also have to specify that the acceleration of the BFCS E as observed by the observer frame E0 is alpha b. So that's what I have written here. And the question is, find P's acceleration with respect to E0, the observer, given that we know all information from the point of view of the BFCS E. So let's do that. In order to do this, we first note that in general E0, the observer frame, and the rotating BFCS may have different origins. Here G and O are different. The origin of E, which is G, is located by a unit vector r g with respect to O, and this vector may change with time. In general, the time derivative of this vector will be the velocity Vg of origin G. The double time derivative of rgo will be the acceleration Ag of the origin of E. With this information, we are ready now to obtain P's acceleration with respect to E0. Before proceeding ahead, let me recall two formulae that we derived in lecture 9. The first formula had to do with computing the time derivative of a vector B, and we computed this in two ways. We said, let d by dt of B be the time derivative with respect to the observer frame, and we related this to the time derivative with respect to the BFCS or the moving frame through this formula. So we said this is equal to B open dot plus omega E with respect to E0 cross B, where this quantity was the time derivative with respect to E, which itself could be a rotating frame. And this formula we are going to use extensively in finding P's acceleration in E0. The other formula that we derived in lecture 9 had to do with relating the velocity of P measured in E0 to the velocity of P measured in the BFCS E, which was Vp rel, and we said this plus a correction term which was omega of B. Remember, omega of B is omega E of E0 cross R P with respect to the origin of the BFCS E plus the velocity of the origin of the BFCS origin G with respect to the observer. So this formula also we derived last time, and let me just make those notes here. So this was velocity observed in E0, while this was velocity observed in ET, and this was velocity of g measured in E0. So, these two formulae we will use now. We want to compute P's acceleration measured in E0. Well, the simple way would be to simply differentiate the velocity of P measured in E0. So, let us do that. So, I take the time derivative of this equation, and the time derivative is taken with respect to an observer in E0 because I want the acceleration in E0. So, this must be equal to d by dt of Vp rel plus d by dt of omega b cross r p with respect to g plus d by dt of Vg. Well, some of these terms are easy. This one is obviously AP. This is the acceleration we are after. The next term, let me just write it out as is, and then we will talk about it. This one I can do differentiation by parts. So, let me do that, and I will get d omega b by dt cross r p with respect to g plus omega b cross d r p with respect to g dt. This is easy also. This is the rate of change of the velocity of g measured in E0. So, therefore, this must be the acceleration of the origin of the BFCS as measured by E0. So, let us write that down plus AG. So, this and this are the same, just like this and this are the same. So, there are several terms here which we need to think about. The easy one is this term. That is because this is the rate of change of the angular velocity of the BFCS as measured by the observer. So, this must be the angular acceleration of the BFCS, which is what I am calling alpha b. So, clearly d omega b by dt must be alpha b. All right. Now, what remains? We need to think about the first term, and we need to think about the third term, which I shall do now. To compute both these terms, we will use this formula that we were just reminded of earlier, where we related the time derivative in the observer frame with the time derivative in the BFCS E through the correction factor, which is this one. So, let us do that. So, let us write down d by dt of Vp rel. Think of this as the vector b. Then by using this formula, so by this formula with b being this, I can write down this to be Vp rel open dot plus omega e with respect to E0 cross Vp rel. I am going to swap these two equations. So, there now I can continue working on the bottom equation. This is the rate of change of velocity of P measured with respect to Et. This is what we call acceleration of P with respect to E. So, that means that this term is AP rel. I can write down now that dVp rel by dt is AP rel, the acceleration of P relative to E, plus omega b. Remember, this was omega b, the angular velocity of the rigid body whose BFCS is E, cross Vp rel. So, let us keep this equation 1. The next term that we had to analyze was this one. So, again we will be using this formula, and then write down omega b cross d r p with respect to g dt. This is what we want to simplify. We identify rpg as our b, and we write down that the term on the left must be omega b cross rpg open dot, that's this term with b as rpg, plus omega e with respect to E0 cross omega b cross rpg. Again, this is the rate of change of p's location measured in this coordinate frame E with origin G and unit vectors EI. Therefore, this is Vp rel. This we discussed in lecture 9 also. This is omega b. These two are the same. So, we can write down this term to be omega b cross drpg dt is equal to omega b cross Vp rel plus omega b cross omega b cross rpg. So, let me call this as equation 2. Finally, we will combine equation 2 and equation 1 with this equation that we had derived earlier, and we will get that AP should be equal to AP rel plus omega b cross omega b cross rpg plus alpha b cross rpg plus 2 omega b cross Vp rel plus Ag, which is what I have over here on the left. And this is the famous 5-term acceleration formula: first term, second term, third term, fourth term, fifth term. So, this is the 5-term acceleration formula. The only comment I have now is that when the origins of E0, the observer frame, and the BFCS coincide, then the acceleration of the point G is exactly 0. So, the special case when these two coordinate systems coincide, which was considered separately when we did velocities, can actually be done as part of this formula. Let us talk a little bit more about this 5-term acceleration formula and get a little more insight into the various terms involved in this.